It is extraordinary how nature can adapt to the ever-changing environment in some very interesting and novel ways. Surprisingly, two very different animals living in two vastly distinct mediums, air and water, have come up with the same solution to navigate, find, track and capture prey in darkness by using a technique called echolocation. These are the microbats and toothed whales, also known as odontocetes. Echolocation, also known as biosonar, is the ability of an animal to view its external environment, navigate and detect food through the use of sound. When a phonation of sound is emitted, it travels until it hits an object in the external environment, which alters the wavelength properties and refracts it back as an echo. The intensity of this modified echo provides large quantities of sensory information regarding directionality and range. The greater the echo intensity, the larger the object is. This information enables the animal to produce a three-dimensional picture of its surrounds. Surprisingly, both species typically echolocate at ultrasonic frequencies ranging between 10 kHz to 200 kHz. Bats are nocturnal hunters and have poor vision, so they rely heavily on echolocation to find food, water, and avoid obstacles in the environment. They echolocate by stimulating a membrane in the larynx and directing the sound pulses through either their nostrils or mouth. Due to the properties of air and the typically very small dimensions of their prey, they must produce higher frequency pulses to create shorter wavelengths to prevent Rayleigh scattering. To overcome atmospheric absorption, however, this method of echolocation is only functional over short distances. Bats vary in their technique and frequency of echolocation, which has led to a variety of specialized morphological adaptations of the outer ear to assist in echolocation reception. In contrast to bats, odontocetes are unique among mammals in that they have the ability to echolocate underwater, and they have excellent vision, which enables them to save echolocation for deep dives, murky or dark water, and hunting. They can produce an array of high-frequency sound pulses by pushing air from their lungs through their nasal passage and pressurizing it. As the air passes through the spiracular cavity, it encounters the phonic lips, causing a pair of ellipsoid fat bodies of the dorsal bursae to part momentarily, then slap back together, producing a sound vibration. A fatty lipid complex in the anterior of the head, known as the melon, can focus the sound energy outwards like a beam in front of the animal. The structure, size, and density of the melon relates to its focusing capacity of the high-frequency, short-duration sonar clicks, as well as enabling the animal to focus its beam to filter away non-essential resonance. The sound pulses emitted by odontocetes can be shorter, travel further, and provide more detail than their echolocating counterparts, the bats, due to the unique properties of water. The returning echo is received through fatty sacs located in the lower jaw of the whale. Amazingly, these two animals have also developed very similar methods for hunting. They both use a three-phase technique, which they switch between broadband and narrowband frequencies for distance targeting and localized targeting. And then finally, they use a terminal buzz technique, which is the increase in emitted phonation speed in order to accurately locate and capture prey. The terminal buzz phase is particularly important for bats, as they have a significantly shorter time period in which to act. The ability to compensate for the Doppler shift is a unique trait of the bat, to prevent it being deafened by its own returning calls during flight. The Doppler shift, as defined by Sheldon, is
the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
This means that the faster the bat flies towards the refracted echo, the lower the required returning frequency needs to be. Although odontocetes cannot utilize Doppler shift compensation, they can use their echolocation along the ocean bed to locate prey buried at shallow depths. Some species of bat almost completely shut down their biosonar sense when searching for prey under leaf litter, and they rely solely on their highly attuned sense of hearing. For both whales and bats, echolocation requires the ability to hear exceptionally high frequencies. It is interesting to note that while having evolved independently, they have both developed a modification of the cochlear outer hair cells. These altered hairs are shorter and stiffer than those of other non-echolocating mammals. Although bats and toothed whales are not closely related, and despite substantial differences in body size and morphology, as well as their respective prey, their evolution has converged with the independent development of very similar echolocation mechanisms.